Today, we're looking at additive manufacturing and the software solutions that are making a significant impact in this field. Our focus will be on pan optimization, a company helping engineers overcome specific challenges in the additive manufacturing process. Joining us today are Tyler Nelson, Principal Engineer, and Eric Denlinger, Co-founder and Chief Engineer. Thank you both for joining us today.
Hey, thanks for having us, Sharon. Appreciate it.
Absolutely. So let's just jump right in. So tell me about pan optimization, how it got its start and when, and what you're up to now.
Sure. The company was founded in 2022. So we've been around for almost 2.5 years now. So the founder, Michaleris, I met him in 2011 or 12 when I was a student at Penn State. And at that time, he was starting another company. He was a professor at Penn State, and he had taken a leave to start a company that he called Pan Computing. And at Pan Computing, we had the first process simulation tool for additive. So it was an FEA-based tool called Cubes, and it gained pretty good adoption in the industry back in that time frame. And then eventually in 2016, we sold Pan Computing to Autodesk, and they took our Cube software and rebranded it as NetFab Simulation. So I worked with Pan at Autodesk for about 5 years. And then he left and retired for a period of time. And then the main motivator, I think, for this company was that he called me up and said that he thought retirement was like waiting around to die, even though he's only in his 50s, so he's maybe a little bit melodramatic. But he wanted to start another company, and we thought there was still a lot of opportunity in the additive simulation space. So that's how Pan Optimization was born. So what we've got is a new FEA solver that we've invented here at Pan Optimization that we call PanX, and it's really the objective with PanX. I say the high level objective is we want to have the maximum possible impact on the industry and generate as much value as we can. And the ways that we see opportunities to do that is by inventing new modeling approaches that allow us to have much more accurate, much more scalable solutions than what have been possible with these process simulation tools in the past. Sometime later last year, we commercialized our new solver, PanX, and we're just in the process of expanding and taking as much of the thermomechanical modeling market for additive as we can.
So can you tell me what differentiates this software that you're working on now from previous solutions?
That's another question that I could provide a short answer or a very we could probably do an hour if we want to get granular on that. I'd say at the highest level, the main differences are that we have a completely new modeling approach that gives us much more accurate predictions for things like distortion, stress, strain, temperature than what's achievable in legacy solutions. It's much more scalable than the legacy solutions. So legacy solutions that were architected, and there's a lot commercially available, they were all architected around the same time frame, that like 2011 to 2015 time frame. They were primarily architected, the objective in mind was to be able to do something that you could call part scale modeling. So there was a lot of simulation, like this guy on my wall here, the GE canonical that you've probably seen before. In reality, that's about an inch tall component, and the goal was be able to predict some distortion trends on that. But then if you take these legacy tools and you try to, I actually have a heat exchanger next to me here. If you try to put a heat exchanger into a model that uses an approach like what you use for that, it's not going to scale. It's not even going to generate an FEA mesh for you. It's just going to crash immediately. So the scalability is really on top of the accuracy is the other opportunity. And then the third thing that I think was really unaddressed in the legacy tools is really not a lot of options for how to optimize outcomes. So they're generally focused on predicting an outcome. They'll tell you that you're in trouble, but there's no really intelligent way to converge towards a solution to get out of your trouble. So I think the accuracy, the scalability, and the optimization are kind of the big pillars that we're tackling here at Pan Optimization.
Yeah, I would just add into that just a little bit. So I was previously a user of some of the legacy tools. I was a fairly big fan of NetFab Simulation, before this code came around. And as a user of the tool and these types of tools, one of the things we just kept running into over and over again was we were trying to really make the tools do stuff that they were never really intended to do. To Eric's point about scalability, for small stuff they were great, as long as you didn't care about something really small like build lines, right? You could model trinkets and small stuff, but as soon as you start to look at full build plates of material or big complicated stuff, which is really where the market has basically dictated that these types of tools go, because that's where all the money is, right? You're not going to be, building, bottle openers. Nobody's paying big money to do that. So,
well, let's get a little granular with this and tell me, like, specifically how your software addresses the specific challenges, such as with thermal distortion and things like that. Can you be a little more specific on how it works?
Yeah, sure. So it's still a FEA-based thermomechanical model, but it on the physics side, to meet these objectives of the larger problems, we've had to include a lot more physics in this. So like the way we would compute temperatures is going to be that has to be redone, the way we compute thermal strains. So it's still thermomechanical modeling, but everything from the included physics, even like the calibration process of the model, all has to be updated. So that's the side of technology that, including that additional physical detail, helps with the accuracy. And then the other side is the scalability, and how that works is we kind of use this as a high level catch-all phrase, but we've invented something that we call multi-grid modeling, which is basically a way to aggressively adapt and reduce these problem sizes on the fly without paying any accuracy penalty. So it's a inherent strain-based model compared on one side, combined with multi-grid modeling that really allows us to get to these truly horrific scales that we can deal with.
I mean, this is a completely new solver. It was basically rewritten from the ground up, and all of these different approaches, first of all, were looked at basically from a parallelization standpoint. So it's extremely parallel. Pan wrote, a lot of the chunks of code many different ways and tested on many different hardwares to make sure it was as optimal as possible. But then really just rebuilding every single building block from the meshing to the strain calculation to how the transient approach works, and all of those different pieces to get something that scales. And then obviously multi-grid was a huge part of that as well. But it's far from the only piece that makes this brand new and unique.
Let's talk about the hardwares that this works on.
Yeah, this is a question I actually get fairly often, especially with new customers. They're excited about the performance, but they come back with a question like along the lines of, if we wanted to buy something that was highly optimized for this, what do we actually need? And they typically assume the answer is going to be either, thousands of cores on some, huge giant cluster, or cloud-based or something like that. But in reality, the way that this software is architected, because it's much more efficient, it's much more memory efficient, as well as just the calculations are very, very fast. You can get extremely good performance on just desktop class hardware. When we do like extremely large heat exchangers and really big builds and things like that, we typically do those builds on high-end desktop hardware with a good amount of memory and fast CPUs. But the really nice thing about that is because we had to invent all of this technology to let us scale to those really, really horrifically complicated geometries, that same technology equally applies to the more standard geometries that are not quite so difficult to simulate, something that maybe could be simulated in a legacy tool. And because those technologies are very, very efficient, we can simulate a lot of the stuff, and maybe most of the stuff that a legacy tool could simulate on very, very big hardware on like a very good laptop. So it basically brings the requirements down across the board, and opens up the high end of the market completely in terms of what just really wasn't possible to simulate at all before.
So let's talk about integration. How does the software integrate with the existing CAD tools that are out there and build preparation workflows that engineers are using for design and manufacturing?
So our view of the solver is it's we kind of think of it as an API, right? It's designed to be plugged into existing workflows. Again, just back to what is the market asking for? They do not want a full-blown interface where you have to reset up everything that you just just assigned in your build prep software. Any information that needs to get passed to the software, our software, is available in whatever your build setup was. So we're establishing partnerships with most major machine OEMs. The most public one so far has been our partnership with Velo 3D, where PanX actually integrates into their Flow build prep software. And this kind of ties back into the accuracy and what's new that's included into the model, but the model can accept a lot of information from the build setup. So the PanX, we build out interops with these build prep softwares where the machine OEM might feed us, like, for example, the energy per pixel that goes into their part. And then they might actually pass us the processing time that it's going to take to process that layer. Since we know where the energy is going and how long it takes, we can start to get extremely accurate thermal predictions in the model that you wouldn't be able to do in a legacy tool. So the idea is to integrate as closely with the build prep softwares as possible, and then pass as much of that build setup information directly from that to the PanX solver.
Going back to the CAD component of that question, so we certainly aren't looking to replace any kind of CAD programs, but once you have a design in CAD, it's relatively easy to export that and either simulate that directly, or as Eric said, pass that through a build prep simulation, which is a processor, which is going to give you the most accurate results. However, I think it is worth highlighting. So with legacy tools, particularly for very complicated things like heat exchangers, if you wanted to simulate that and have any chance of success on an older tool, the way you would typically do that is you would model the geometries twice, which is very, very painful, especially for big ones. So you basically model it once in full detail, and then you model it again, cutting out maybe the core, cutting out those fins or something like that, so you can approximate that using homogenization manually, essentially. So that's one of the big differentiators when it comes to these big giant models that we're able to simulate, is we don't need those simplifications to be done. We take the original CAD with the full detail. And if you want to do some aggressive approximations, aggressive homogenization, you can do that automatically with a single line in the code. But if you want to include all of that detail, you can do that just as easily. And that's a huge advantage, not to have to model these things twice and export twice and put up twice and all of that.
What about user friendliness? How easy is it? How user friendly is it for your software to be used by engineers who might not be experts in simulation? And then that would, of course, lead to what training or support do you provide?
It's very user friendly because so much of the meshing, setting up the FEA problem is done automatically. Either for the powder bed, it's done automatically based on the geometry, and for the DED problem, it's done automatically based on either the geometry or the toolpath. So that takes a lot of the pain out of the setup. So the learning curve is a very, very, very small fraction of learning like a general purpose FEA code, like an ANSYS or an Abacus. We have a good part of the user base are people without an FEA background. For those people, we have a very simple UI that's it's basically form based, where it's what's your geometry, what are your parameters, all phrased in a way that you don't have to have any modeling background to understand what the inputs are. In terms of training, we offer for people that start to use the software, they get a free training session with Tyler, who has 15 years experience doing this type of a setup, and they can pretty much reach Tyler or somebody here whenever needed for assistance using the thing.
I would add to that a little bit. So I do most of the trainings, and I think typically within an hour or so, people are very comfortable to start running stuff. Are they an expert yet? No. But they know enough to be dangerous. And
you can get yourself in some trouble after an hour. Yeah.
And we encourage, semi-infrequent, or initially it might be fairly frequent check-ins, where we might just pair together on a problem, and they'd say, hey, Tyler, how would you set up this part? These are the things I'm looking to get out of the model. And we can kind of give them a more optimal way to start from. But the other thing that I would like to highlight, just because it means a lot to me personally, is we really have a different approach of the customer service and the training at this company than I really have seen anywhere else, in that one of our goals with new customers and new companies is to really make sure we have at least one expert at the end of the day that can really take over a lot of that day-to-day questions that people, as adoption grows. through the company. So we spend a lot of time up front, at our own cost to really make sure that at least one person is very, very comfortable and even approaching expert level in the tool. But even beyond that, we're very responsive with questions.
All right, let's move on to validation then. How do you validate to ensure that simulations provided by the software actually correlate with the real world outcomes?
That's a good question. So this is this is a tedious and expensive process. I think first of all, I'll say we're fortunate that this time around, I think we are fairly well known in the industry. So we've had very good luck lining up partners, whether machine OEMs or end users that are willing to build stuff for us to validate these things, which has eased a lot of the burden. Plus, there's just a lot more published data on these things. So the basic validation methodology really depends on what output from the model you're validating. So the first I'll touch on temperatures. So the temperature validation is done with in situ thermal measurements. So we actually have thermal cameras in these machines that are taking pictures of the deposition right before you start to laze the next layer. After every layer basically generates like a composite image of all the starting temperatures for the whole build. And then you run the models and you compare it over the whole duration of the build to make sure you're matching that evolution of the interlayer temperatures at different locations. So that's actually more on the more tedious end of the validation spectrum. The distortion validation is a little bit easier because that's typically done post-process, where you take a white light or a blue light or a CMM measurement of how a part actually deflected, and you compare it to what the model predicted. So we're constantly that the validation is very intertwined with the development of the product. Like the starting point for any model is we want the simplest model possible that's going to meet the objective. We make that, we compare it to reality. If it doesn't match, you think, well, what else needs to be included in the model to get the match? That's where things like machine parameters or timing and things like this. Okay, well, what if we include that? Does that how much better does that make the prediction? Does that achieve the objective? If not, what else can we include in the model? So it's always that question of how well is this agreeing with reality, and is that level of agreement adequate to meet the objective is what drives all of the modeling decisions.
Yeah, I would say that it's an iterative process and it evolves over time. I mean, when you first start out, maybe you have less data and you get more data over time. And we definitely see this as a huge advantage for, working with the different machine OEMs like Velo, for example. And, they're very interested in tight tolerance compensation. And so they might, come to us periodically and say, this is working really well, or maybe this is a little bit not as good. The temperature is a little bit off. Help us understand why, and then they'll pass that data back. We can do a deep dive on it internally and try to understand which modeling assumptions are driving those differences, and then ultimately arrive at a better model.